Okay, so and I'm going to let's see. I need to remember how to hide the floating meeting controls. There we go. Uh, that's not the right size. There we go. Okay, I'm going to start off by very briefly reviewing the two mini summaries from last time, just in case that might be helpful. So last time I defined light front coordinates using one of multiple standard conventions. So the light front coordinates are always defined in terms of an x plus and an x minus, which are known as null coordinates or light cone coordinates. One of them is going to be t plus z or x0 plus x3. That's x plus, and x minus is defined as t minus z or x0 minus z. Where conventions differ, these sums or differences might be multiplied by a factor of either 1/2 or 1 over the square root of 2. And I'm using a convention with 1 over the square root of 2 because that just makes a lot of the algebra work out very nicely. Uh, you end up having very similar looking inversion formulas, for instance. The metric tensor is a lot nicer. And when you define things like the invariant four product, you end up having no factors of 2 or 1/2 in it. So x dot y is x plus times y minus plus x minus times y plus minus the usual vector dot product for the transverse components, which are your x1 and x2 or y1 and y2 components. Your canonically conjugate energy and momenta are given by p minus is conjugate to x plus, p plus is conjugate to x minus. This works out automatically, and your convention for raising and lowering indices is that a four-vector component with a lower plus is equal to the component with an upper minus, and lower minus is equal to component with an upper plus. We choose for x plus to be time. This is also a convention. You could, in principle, use x minus as time instead. It's equally valid, but most people use x plus. And because x plus is chosen to be time, that means p minus, p with an upper minus, is energy, since that's the conjugate variable. And verbally, when someone says X plus, they mean X upper plus. So we prioritize the contravariant or upper index form when we're verbally referring to components. And one of the really nice things we saw, and I'm hoping today to get to a deeper explanation of this, is that a lot of formulas you encounter in light front coordinates look similar in form to non-relativistic formulas. Like your energy, which is P minus, can be written in terms for a non-shell particle as uh, an m squared over 2p plus plus a p perp squared over 2p plus. The second term looks kind of like a kinetic energy term from non-relativistic physics, but with p plus there instead of mass. And your components of momentum, uh, the four momentum p minus and p perp, are equal to p plus times the velocity in the minus and perpendicular directions. The other mini summary uh, regarded conceptualization. Light front coordinates basically describe space-time as we see it, at least when we're looking in a particular direction in the plus z direction. When we see distant events, we consider them to be in the present instead of the past. Basically, everything that is traversed by a single light front uh, that comes and hits our eyes is considered simultaneous. Longitudinal boosts produce observed redshifts and blue shifts instead of time dilation when you apply the formulas for how longitudinal boosts transform things in the light front. And what we would normally call a transverse boost produces the observed Terrell rotations instead of Fitzgerald contractions. Additionally, we can define what we call a light front transverse boost, for a very small, for an infinitesimal transverse boost, as consisting of what we would normally call a transverse boost plus a counter rotation that undoes the apparent Terrell rotation. This leaves the transverse spatial structure of what we're looking at invariant. Uh, are there any questions regarding the mini summaries? If not, I'll move. Oh, yes.
Hi. So here the generators of this transformation is dy is 1 over square root of ky minus jx. So I just wonder why jx, because jx and jx, it is the generator of rotation in yz plane, right?
Yes.
So y should can also be there, right?
So the reason that it's JX is because if you boost something in the Y direction by an ordinary Y direction boost, then the observed Terrell rotation is in the ZY plane. So in order to undo the Terrell rotation, you need to do a rotation in the ZY plane. So that's a rotation around the x-axis.
Yeah. Sorry. Okay. Thank you. Yeah.
So I'll move on to stuff about finite boosts and kinematics next, because the transverse boosts I've been looking at so far have been infinitesimal. So, first of all, before actually looking at the finite boosts, there's a really amazing thing that happens with these infinitesimal boosts, with these generators. If you take the commutator between them, then you can just use linearity of the commutator. You get four terms. Uh, there's your commutator between the ordinary infinitesimal boosts in the x and y direction, which induce a rotation around the z-axis. And you have a commutator as well between the jy and jx, which also, by the standard commutation formulas, give you a rotation around the y-axis. On the other hand, the x direction boost and rotation around the x-axis commute similarly for the y-axis. Uh, but these two commutators that give you a infinitesimal rotation around the y-axis come in with an opposite sign, and they cancel out. So what we call the light first front transverse boost generators commute with each other. This is one manifestation of what's called the Galilei or Galilean subgroup of the Poincare group, which is also responsible for all the classical looking formulas that we've seen so far. So before moving on to fleshing out the full group, I want to look at finite boosts because that will give a bit more intuition as to these classical looking, non-relativistic looking formulas. So I'm going to go into a little bit of the basics of Lie algebras and Lie groups now. So generators are basically things that quantify infinitesimal transformations. So you have a finite boost by a finite velocity. Uh, for any transformation, you can approximately, for very small velocities, in this case, uh, approximate it as kind of an infinite series in the parameter that you're transforming by. Of course, the leading term is 1, because if you don't transform anything, you just multiply by 1. And then you have a linear term, and then higher order terms potentially. Uh, the coefficient multiplying v in this linear term is called the generator. By popular convention, we usually also pull out a factor minus I here. I personally, in my own notes when I'm doing calculations, like to not have this factor minus I. I consider the minus I to be part of the generator when I'm doing my own calculations, but nearly everyone else pulls out this minus I here, so I'll just use the standard conventions in these lectures. So in order to get generators, you would look at what a finite transformation is. So for instance, a finite boost in the x direction, standard boost, you can write it in terms of your rapidity eta using the hyperbolic trig functions. So cosh eta is the same as gamma, sinh eta is the same as beta gamma. So for an active boost, for passive boost, you would have minuses in front of these cinches. For an active boost, it basically just takes this form. You have this diagonal coches, off diagonal cinches, and for the axes, you're not looking at just multiply by one. So you would expand this as an infinite series in eta and keep only the linear term. You would subtract off the one. So cosh eta to linear in eta is just one. So all the diagonals become zeros. Sinh eta to linear in eta is eta. Uh, so you pull out a factor minus I, you get an I, and that's how you get this boost generator. Similarly, for a rotation around the y-axis, you have your cosine thetas. For the on diagonal, sine theta minus sine theta for the off diagonals. You expand to linear order, the cosines become just one. You subtract off all diagonals one. The sines are theta, and you pull out a factor minus I, which will give you an I here and a minus I here. And as usual, once you have these matrices, you can use what we called the C matrix in the previous lecture to convert a matrix from instant form to light front so that it tells you how these generators transform x plus, x perp, and x minus instead of x zero, x perp, and x three. If you work out the algebra, then you end up getting something that actually looks a little bit more complicated. In instant form, we just had two non-zero components. Now we have four non-zero components, all with square roots of 2 over them. This might look like a case of light front being a bit more complicated, or the 1 over square root of 2 convention being more complicated. But that's because this generator, this KX generator, actually isn't the ideal thing to use in the light front. We'll see things coming out a lot nicer very soon. And you can do something similar for the generator of rotations around the y-axis. You just multiply on both sides by the C matrix, work out the matrix algebra, and you turn a simple looking thing with two non-zero components to a more complicated looking thing with four non-zero components with some square roots of 2 everywhere. But then we remember that what we call a transverse light front boost is a combination of a traditional boost and a counter rotation that cancels out the Terrell rotation. And it turns out that some of our components very nicely cancel. Uh, So I do have a typo here. There should not be a 1 over the square root of 2 multiplying this entire matrix in purple. Uh, we had square roots of 2 here. A square root of 2 in bx is kx plus jy over root 2. So those multiply to become 1/2. And you're adding 2 of the same thing from kx and jy. So you get 2 times 1/2. So it'll just be 1 multiplying it. So this 1 over square root of 2 here shouldn't be there. That's a typo. I'll fix it in the official version of the slides that will eventually be uploaded. But you end up again with 2 non-zero components that are just imaginary. So this BX, this generator of finite light front transverse boosts, is actually very simple in terms of light front coordinates. But something else really amazing happens with this. The components that are non-zero are kind of like not reflected around the diagonal from each other. And if you square this matrix, instead of getting something with two non-zero components, you get something with one non-zero component. If you cube it, then you get zero. All the components become zero. So obviously fourth, fifth, sixth, and so on powers are also zero. So the technical term we use for it is that this generator is nilpotent. That means there's some power of it that exists that will give zero. And this power in this case is three. The really neat thing about nilpotency is that, uh, well, the way you build a finite boost is kind of like how you would continuously compound interest. You just apply lots of infinitesimal boosts. You consider a very small boost by your actual target velocity divided by the number of boosts you want to perform. You perform that many boosts, and you take the limit of the number of boosts you're performing to infinity, and you get the formula for a finite boost that way. So it's just exponentiation. But because of the nilpotency of the generator, you can expand your exponent as an infinite Taylor series using the standard formula, and the Taylor series terminates because bx to the third and likewise by to the third are both zero. You end up with just a three-term series, which is exact, which is actually really nice. It makes a lot of algebraic calculations in terms of these light front boosts really simple. Another really neat thing that you can check by just multiplying these bx and by matrices is that they both multiply to zero. So not only do they commute, bx times by is also zero, which makes the algebra really simple when you want to perform both x direction and y direction light front boosts. So because you have this really nice three-term series, the way that you transform a four vector is, in terms of light front components, is you multiply by these matrices and by vperp, and they end up just mapping the time component, the x plus, into something. Uh, this is the fact that your component in the leftmost column and it for bx and the row corresponding to x for by and the row corresponding to y is non-zero. And you get a contribution to x minus, which involves dotting p perp with x perp. You can see that by looking at the last row. You have a non-zero component in the x column for bx, for the y column for by. This all multiplies minus I, so you end up getting plus. And for the square of either bx or by, which are the same, your only component is in the column corresponding to x plus, the row corresponding to x minus. So it maps x plus into x minus. So it's a really neat thing. And this automatically guarantees then that it leaves time invariant. It can map time into other things. You get a formula that looks like your standard, well, now you're moving with a linear velocity here. Uh, but things work out very nicely because of these simple nilpotent forms of these matrices. Another really nice application of this, I'm going to combine now the light front transverse boost with a longitudinal boost, is that you can reach any momentum from rest using these boosts that leave light front time invariant. So first, what you would consider to be rest in terms of light front coordinates, well, in instant form, it's just that the energy is m. components of momentum are zero. You can multiply this by your C matrix, and you would find that your rest state is one in which the P plus and P minus components are both m over the square root of 2. You can also reach this conclusion by just noting that P plus and P minus are energy plus or minus Pz over the square root of 2, and at rest, the energy is m and Pz is 0. So you get this kind of symmetric looking formula. And then from there, you want to apply a longitudinal boost by some rapidity eta and a transverse boost by some velocity v perp. So the first thing we're going to do is the longitudinal boost. We can have our longitudinal boost generator. It just has off-diagonal I components in instant form, and we sandwich it between the C matrix. And if you work out all the matrix algebra step by step, I'm not going to walk you through it. Uh, you get two non-zero components, which are both diagonal, I in the upper left and minus I in the lower right. This is really neat because when you exponentiate it, you end up getting e to the eta for your top left component, e to the minus eta for your bottom right component, and for the other diagonal components, you just have one. Of course, a boost in the z direction leaves x and y invariant. But boosting along the z direction basically just means that you scale your plus and your minus components in opposite directions. So this is actually really nice. And if you boost from rest, uh, your forward momentum basically gives you a P plus that is proportional e to the eta, a P minus that's proportional e to the minus eta. Proportionality constant is m over the square root of 2. So you have this very nice scaling behavior. This also allows you to determine what the rapidity must be in order to get a particular target P plus. So it's just going to be the log of this combination, P plus over m times the square root of 2. Another really neat thing is because P plus is invariant under finite transverse light front boosts, the ones that have the Terrell counter rotations under them, not the traditional transverse boosts. Once you reach this target P plus, your finite transverse boosts will not change it. So this is actually the reason that we do the longitudinal boost first. As for the transverse boost, you have this finite terminating series, and you can use the boost generator matrices that I showed a few slides ago, actually contract them with the x and y components of your perpendicular velocity, and you get this really nice lower triangular matrix. All ones in the diagonal, but you have some Vy and Vx components and even a square in the off-diagonal lower components. So if you take your forward momentum that has been boosted longitudinally so far and you boost it transversely, you get a formula that can be written in terms of eta and v like this. The bottom component looks a little bit messy, but if you write everything in terms of P plus instead of e to the eta, you see your formulas that look like non-relativistic formulas. You have a momentum that's proportional to Vx and Vy for the transverse components, but with P plus as your multiplying factor. You have basically something that looks like kinetic energy in your P minus or your energy component, 1/2 of P plus V perp squared, with P plus instead of your mass. You have a term for which you have energy even when you have zero transverse velocity, of course. Uh, So we recover all the classical looking expressions by boosting a particle from rest using just these nice light front boosts. So basically, the reason that these non-relativistic looking formulas show up is because we're able to boost a particle from rest using these light front boosts. So the summary so far is that the finite boosts on the light front, if you're at least if you're using the non-ordinary light front boost for the transverse one, take simple forms in terms of light front coordinates. The longitudinal boost is diagonal, so it just involves scaling your plus and minus components of a form momentum. And your transverse boosts are lower triangular, and the diagonal components are all ones. So these are really nice. Uh, the generator for the second is nilpotent, so the series from exponentiating the generator terminates, which is the reason that this finite V perp works out so nicely. And momenta can be written in a very classical looking form, with P plus appearing where the mass would. The mass, of course, is still a thing that is there, but is different from P plus. And this occurs just because of how you can boost from rest to any target momentum. So that's the summary of the finite boosts and kinematics section. I'll go a bit more into group theory in the next section, but in the meantime, I'm willing to take questions if there are any. If not, I can move on.
Adam, this is James Very.
Mhm.
I have a question after this beautiful and elegant introduction to the kinematics and invariance properties of the light front. Often you hear colleagues talk about, oh, that's just the infinite momentum frame in a different language. But you, I think, in your first lecture said they are distinct. Is there a convenient point you can make now about, what is it that makes the distinction obvious between working in the infinite momentum frame and working in the light front coordinate system?
I think the thing that actually makes it the most obvious is that you can start from rest and boost to any momentum. So you can actually describe systems that are at rest using light front coordinates. You end up having a funny looking formula with two non-zero components. And you can boost to infinite momentum. Uh, Typically, people mean the infinite momentum frame as one in which P plus is infinite. You just take eta to infinity here, and then e to the eta becomes infinite, e to the minus eta becomes zero. So you can describe things in terms of the infinite momentum frame by starting with light front coordinates, just as you can start from instant form coordinates, but you can work in any reference frame.
Thanks.
Yes, hello, good morning. If I can just pick up on what James said.
Mhm.
Very early on, the infinite momentum frame was introduced by Weinberg in order to simplify Feynman diagrams, and it was discovered that in light front you got the same simplification. That's where the connection comes. But light front holds in non-infinite momentum frames as well,
Mhm.
and that's where the real advantage is.
I
That's
agree with that. I guess another interesting thing that happens is that if you're in instant form coordinates, then P0 is your energy. And when you boost to infinite momentum, P0 becomes infinite as well, so your energy becomes infinite. If you boost to infinite P plus, then P minus scales the opposite way and actually goes towards zero. So in the infinite momentum frame, your instant form energy becomes infinite, but your light front energy becomes zero. So you have some differences between light front and instant form, even in the infinite momentum frame. That's another thing that I think that this section kind of shows. Another kind of tangential thing that it's more of a qualitative or conceptual thing, I guess, is that people like to talk about partons being frozen in the infinite momentum frame. If you use light front coordinates, then your Hamiltonian approaches zero. So that's your time translation generator. So conceptually, it kind of makes sense to think of time as being frozen in terms of light front coordinates when you boost to the infinite momentum frame. Though, of course, that's a perk of combining the two. You can always use light front in any finite momentum frame. There's another question?
Yeah, so could you comment on what will happen if one takes the Galilean transformation in just conventional Minkowski space? I mean, yeah, so how the formulas looks in that frame?
So that's a good question. I have not actually done that calculation because I assumed that it would be extremely messy in terms of ordinary instant form coordinates. Uh, I guess that could be kind of a nice exercise. So I have here, you have these nice formulas for the generators in terms of finite transverse boosts. Or sorry, you have these in terms of light front coordinates.
Yes.
So because with the square root of 2 convention, the inversion formulas are identical to the conversion formulas, you could convert these to instant form coordinates by multiplying on the left and right by the C matrix. And in fact, since the C matrix squared is 1, you could also do that for the finite boosts. So you can take this finite boost matrix, multiply it on the left and the right by the C matrix, and that should give you the formula for doing the transformation in instant form coordinates. I have not done it, so I don't know exactly what it would look like, but my gut feeling is it would look extremely messy.
And the one another query. So if one takes this conventional, I mean, Minkowski's or this Poincare transformation and put gamma equal to 1, then do they will look similar? I mean, this is what one expects naively.
So gamma equals to 1. You would get that only when you're not doing any boost at all, right?
Yeah. Yeah, but
So this generator, this light front transverse boost, the generator involves having both a boost and a rotation. So the only way that this V perp can be, the only way that your boost can have gamma of 1 is if the V perp is 0. So you just get the identity matrix.
I guess one has to do this thing. Yeah. Thank you.
Yeah. It's just a different transformation than the ordinary transverse boost.
Yep. Thanks.
Okay, so this is kind of the section I've been working up towards. As a disclosure, this is probably going to be a lot math heavier than the previous sections. It's not going to be like really deep math. It's not going to be like an intro to topology class or anything. It's just going to be a lot of algebra. The motivation here is that the Poincare group has a 1 plus 2 dimensional Galilean subgroup. X plus, what we've been calling time the entire time, acts like time under this subgroup, and X perp acts like space under this subgroup. And what we've been calling P plus is a central charge. Basically, it's a generator that commutes with the rest of the subgroup. And both X plus and P plus are invariant under the subgroup. P plus being invariant is kind of logically equivalent to it being a central charge. But X plus transforms the same way as P plus, so it's invariant. Time being invariant under transformations is an important part of, well, it being a Galilean group. So basically, using light front coordinates, light front time instead of instant form, gives you an exact, fully relativistic picture that, in terms of 2+1 coordinates, looks a lot like non-relativistic physics. You have things that look like some of Newton's laws, kinetic energy formula, something that looks like P equals mv, except you have a P plus instead of an m. You have commuting transverse boosts. Very Galilean, very non-relativistic looking, but this is all exact and fully relativistic. So now we're going to get a bit into the weeds. The Lorentz group is a subgroup of the Poincare group, so we're not including space and time translations, just boosts and rotations. There are 6 generators to this group overall, 3 infinitesimal boosts and 3 infinitesimal rotations. So we often can write in a covariant form the generators using Greek indices. So you have m mu nu. The generators are anti-symmetric, so it's equal to minus m nu mu. So of course the diagonal ones are 0. You're left with only 6 independent generators. But yeah, boosts in your 3 directions, rotations around your 3 axes. And your boosts are equal to the m0I uppers. Have to be careful with all this raising and lowering and exchanging indices because you get minus signs. I actually made a bunch of mistakes in the process of preparing these slides. Very easy to make sign mistakes if you're not careful. And your rotations, say a rotation around the x-axis is a rotation of the y and z axes into each other. So J1 is M23, and similarly for the other rotation generators. The overall algebra is defined by a commutation rule. It's kind of a ugly looking thing, a helpful mnemonic. I was actually going to have something pointing to some indices pointing out the mnemonic, but it seems I did not do so. I'll correct the slides when I post them online. But basically, for your first term, you take the metric with the first indices of both of the things you're commuting with each other, so mu and rho, g mu rho, then the last indices of the 2 things in your m, then last and first, then it's outer and then inner, then outer, and for the minuses you have first, last, and last, first. So little mnemonic, you have to just remember that it's outer, inner before first, last. Now, I'm not going to step through deriving this rule. There are 2 ways that you can do it. You can use what's called geometric algebra, basically Clifford algebra, or you can say that there's some linear coefficients. You don't know whether they're +1, -1, I, whatever, A, B, C, and D. But we know that 2 boosts need to induce a rotation, or we know what the basic algebra of rotations looks like. So we can require that this covariant commutation rule reproduce these more explicit forms below. Either way, you can derive this rule. So, as kind of a little algebra exercise, let's at least prove that the boost rule follows from this general covariant rule. So your fundamental rule, I've colored the 4 terms here. And if you work it out for the boosts, so you have Ki is M0I, Kj is M0J. You take the outer indices first. So 0j off diagonal. This is in terms of instant form coordinates is 0. So you get this term drops out. This parenthesis should be next to this I. I is multiplying everything. I'll correct that as well. That's just a typo. Similarly, you get 0 off diagonal for this purple term. For this blue term, you have the first indices from both G00, Mij. So this is going to be a rotation and it's non-zero. And for the last term, you get two zeros here. The first index of both 00. M000 because these generators are antisymmetric in their indices. So you are left with just two infinitesimal boosts turning into an infinitesimal rotation. And you end up getting the correct minus sign as well. You can similarly prove the rotation algebra formula from the more general rule. So this is kind of just a sanity check that your more general rule reproduces the known commutation rule for rotation generators. The proof is a lot more involved. I'm not going to step you through it because that would take a little bit of time, but it's worth kind of working through it for yourself. And after I fix the typos, I guess I'll give a preliminary version of the slides to Wally to post online for anyone who wants to take advantage of the steps that I did here. And you can similarly prove the commutation rule between boosts and rotations a lot easier than rotation plus rotation. You end up getting a couple of zero terms. You end up reproducing the boost. I won't step through that because that would take a little bit of time. Now, you can, instead of writing in terms of 3 instant form boosts and 3 rotations, you can take your same 6 generators and write them in terms of light front coordinates. So now I'm going to take a different approach than I have been so far, where instead of trying to define the generators using conceptual arguments, I'm just going to take plus and minus components of things. So your boosts are, instead of taking oh, wow, that should be m+1 here for this first one. There's a lot of typos in these slides. I need to fix them. So whereas in instant form, we were defining our boosts using M01, M02, M03, since plus is time instead of 0, this should be M+1, M+2, and M+- will be our 3 boosts. And our 3 rotation generators, instead of M23, M31, M12, will be M2 minus, M-1, M12, because by fiat, we're considering x minus to be space and x plus to be time. The same covariant commutation rule follows. That's covariant after all. However, when we use plus and minus as our indices instead of 0 and 3, we get these commutation rules instead. Our transverse boosts, we can prove that they commute. Our rotation around the z-axis, which I've here marked R minus, rotates things, rotates the x and y components of our rotation boost generators as if they're two-dimensional vectors, so that's kind of nice. And our rotation around the z-axis and our longitudinal boost commute as we expect. We also have our boost along the minus direction or the z direction, does not commute with our transverse boosts or our rotations, kind of weird transverse light front rotations, but they do commute with transverse boosts and they commute with each other. That they commute with each other is actually pretty weird. So let's prove the boost formulas at least. Bi and Bj commuting is something we saw previously when we used conceptual arguments to define them. We have our very general rule. if we allow I and j to not just be 1 and 2, but also minus, so we can get everything in one go, well, for our green term, the mnemonic is we have outer indices going into our metric, inner indices going into our generator. And for purple, it's reversed. Inner for metric, outer for generator. And you have G plus and something. This is off diagonal, but if J is minus, our light front metric is off diagonal, so G plus minus is 1. So basically, can be written as like a Kronecker delta. It's 0 unless J is minus. Similarly, for the purple term, 0 unless I is minus. For the blue term, we put the first index of both generator into the metric, so we get G plus. But because the light front metric is off diagonal, G plus plus is 0, this term's 0. And similarly for our last term, the red one, we put the first index of each into the new generator, and n plus plus is 0 because, well, that's just antisymmetric. So we end up with 3 possible cases. If neither I nor j is minus, then we get 0 from our commutator. So our transverse boosts commute. If I is minus, we get the purple term survives. You get I, bj. And if I is minus instead, then we get minus. And of course, both I and j being minus would mean they commute because you're commuting something with itself. That's always 0. So in the case of j being minus, you can turn it into something where minus is the first component by just swapping them around. And you get a minus sign. So basically the rules we get are the transverse boosts commute, and the longitudinal boost basically kind of rescales the transverse boost. We can also prove the commutation rules. This actually I'm not going to step you through, but it would be a good idea to kind of step yourself through it later when you have if you have time. And another really nice thing is that the rules involving the r minus rotation between the x and y axes. Excuse me. If you take the commutator of r minus with one of your transverse boost generators, then you end up just getting another transverse boost generator. So if you commute it with B1, you get I times B2. If you commute it with B2, you get minus I times B1. So it's basically just kind of a cross product with, say, a unit Z vector. So I didn't include step-by-step derivations for all of the rules. I'm leaving the rest of them as an exercise for you. It's worth doing. Working through the rote algebra does help give you intuition for working with these light front variables. So once you actually get all of these rules, and it is worth going through the algebra and getting all of them, then your instant form versus light front looks a little bit more complicated. With instant form, you can summarize things in terms of just 3 formulas. Light front, you have a few more formulas. You have your, excuse me, you have that your transverse boosts commute, your rotation around the z-axis rotates the boosts into each other. You have these other formulas, and you have a bunch of things that you don't have to write down because you have a lot of things that commute with each other. So all of the other ones commute with each other, which is actually kind of nice. You can derive a bunch of these relationships just from index manipulation as well. So for instance, previously I made a conceptual argument for why the generators of light front transverse boosts had to involve these peculiar combinations, kx plus yx or ky minus jx, based off of canceling out a Terrell rotation that you would observe. However, just by manipulating the indices, by just saying that, oh wow, this is a typo, this should be m plus I. Too many typos on this section. Well, you can write m plus I as m0I plus m3I over the square root of 2. m3I can be written in terms of your rotation generators, and you end up getting exactly these same formulas that you got conceptually just from doing index manipulation. So this shows a consistency between the rote algebra and the conceptualization. So they're two sides of the same coin. They're both ways of looking at the light front, and I feel like it's really fruitful to both be able to prove things using just the algebra and to be able to think about things in a conceptual way. Being able to do both makes light front feel a lot more natural and intuitive. Now, this is only the Lorentz group so far. That's just a subgroup of the Poincare group, and these blue formulas here are only a subgroup of the Galilei subgroup. So the Poincare group as a whole has 10 generators. In addition to the 4 Lorentz transformation generators, you have 4 translation generators, which are just given by your 4 momentum. The algebra is given by commutation rules. You have this one that we've been playing with the last few slides, and there's also a commutation rule between the Lorentz generators and the translation generators, and the translation generators commute with each other. More explicit rules that you can derive in instant form, I'm leaving that as an exercise, are written here. Now for light front, again, I'm going to leave this as a exercise for you to show. The full Poincare group consists of a lot of formulas. It can't be summarized in as few formulas as instant form. One of the downsides of light front is, well, more formulas, just because of how you're treating one spatial direction different from the others. But a lot of these formulas are 0, and you have some fairly simple looking things for all of your particular little formulas. The ones on the left are not part of the Galilei subgroup. The ones on the right are part of the Galilei subgroup. These red formulas here are telling you that some of these generators do not commute with P+. The Galilei subgroup is the subgroup that leaves P+ invariant, and these red formulas are the reasons that B- and Ri are not part of the Galilean subgroup. However, the rest of these formulas are part of it. In fact, these last 4 formulas are just telling you that all of these things in this subgroup commute with P+. So, the rest of these slides will just be kind of more conceptualization or some math regarding this subgroup. What's in the subgroup? It involves your transverse light front boosts, which commute with each other. It involves your rotation around your z-axis, or equivalently, rotation around the x- axis, with x plus fixed. It involves your translations in your transverse plane. It also involves your Hamiltonian, and it involves P+, since it commutes with itself and everything else in it. It's kind of like a mass in that your mass commutes with everything in non-relativistic physics. So that's 7 out of 10 generators. That's actually a pretty big subgroup. The things that are not in the subgroup are the 2 things that, shown in red, do not commute with P+. So that involves your longitudinal boosts. They change P+. In fact, the longitudinal boost is how you get from your mass to a target P+, so they fail to commute with it. And rotations around the x and y axes reorient the light front. So, of course, they change P+. Basically, anything that fails to commute with P+ isn't in the subgroup. But it's a big subgroup, 7 out of 10 generators. It's not bad. A bit of intuition, why it's called the Galilei subgroup, why it's comparable to 2-dimensional non-relativistic physics. Well, in 2D non-relativistic physics, what you have are 2 translations, 1 rotation, 2 boosts, 1 Hamiltonian time translation generator, and 1 mass. Typically, people don't think about the mass as an operator, but if you promote it to an operator, then it's just an operator that commutes with everything else. So that would give you 7 total generators. All the non-zero commutators are written here. Your rotation, well, it transforms your translations and boosts as if they're two-dimensional vectors. Your boosts will change your momentum in a way proportional to your mass, P equals mv and all that. And your Hamiltonian does not commute with your boost because your boost changes your energy. If you look at the Galilei group in 2D light front physics, you have your 2 translations, your rotation, your 2 transverse boosts, your Hamiltonian, which is P minus, and a longitudinal momentum. And that's 7 total generators. And if you flip back and forth between the 2 slides, it's exactly the same algebra. So this is basically the reason that you have so many formulas that look like non-relativistic formulas in the light front. It's because you have exactly the same group algebra, same group theory, same algebra there. So that's pretty neat. So this is another neat thing. Actually, this idea is something that I learned about from a lecture that was given, I want to say a year ago at this point. Was it a year ago or a few months ago? No, I can't remember. It was given a recent summer by Cedric Lorcet. You can actually use your boost operators to define a transverse position operator. This is really neat. So look at all the non-zero commutators here and look at the algebra that you would expect a position operator to obey. The position operators have to commute with themselves. Their commutator with the momentum should give you just I times a delta function, and you have your Heisenberg equation. The commutator with the Hamiltonian should give you your velocity. And actually, the really neat thing is that you take your transverse boost minus your transverse boost, divide it by P plus, and this satisfies all these commutation relations. It has the same algebra as a position operator. That's really neat. Learned about that from a lecture by Cedric Lorcet. So exercise for you to prove using this is the purple commutation relations. So actually, I will at least go through this last one. Oh no, I won't go through this last one. I'll go through proving that it's boost invariant. So your transverse position operator. Recall the following commutation relations from your Galilei subgroup. Transverse boosts commute with each other. Transverse boosts commute with P plus. That's one of the defining features of the Galilei subgroup. Oh yeah, and your longitudinal boost is not part of the Galilei subgroup, but some of the algebra for it is really important. B minus, when you commute it with Bi, you just get I times Bi, and B minus, when you commute it with P plus, you get I times P plus. So, simply enough, if you do a transverse boost to your position operator, then you can use this nice rule for commutators of products. Commutator of A with BC is equal to B times commutator AC plus commutator AB times C. So X perp is going to be a product of P plus to the minus 1. So basically the inverse of P plus times Bj. You can actually put this on either side. Works just as well since P plus and Bj commute with each other. So you use this relationship and you get 2 terms, a commutator of Bi with Bj, a commutator of Bi with P plus to the minus 1. Since Bi commutes with P plus, it commutes with its inverse as well. So both of these commutators are 0. The transverse position commutes with the transverse boost. There's a little bit more algebra for showing that the transverse position is invariant under longitudinal boosts. You use this same nice relation for the commutator of A with BC in order to break things into 2 terms. Then you have a commutator of B minus with P plus to the minus 1. There's another neat little relation you can show for commutators, that the commutator of A with B to the minus 1 is equal to minus the commutator of A and B, but then sandwich on both sides between b to the minus 1. So you end up getting something that involves a commutator of b minus and bi. So you get I times bi with that. And because of the minus you get from this relation, you have a commutator of b minus with p plus. You get I times p plus here. You get two terms that cancel each other out. So the transverse position commutes with a longitudinal boost. So this is a really nice thing and will actually be a lead into my next lecture in 2 weeks. The perpendicular component of your or rather your perpendicular position operators commute with all of your light front boosts. So because you can reach any momentum by a sequence of these light front boosts, and because these light front boosts leave transverse position invariant, you have a way of getting a system from rest to any momentum that leaves the transverse spatial structure of the thing you're boosting invariant. This means that the light front will provide you with a transverse spatial picture that is quantum mechanical because you have canonical commutation relations for x perp and p perp, applies to relativistic systems, and is invariant under motion. Ultimately, formally, it's a consequence of the Galilei subgroup. Or if you want to think about things conceptually rather than algebraically, you can think of it as a result of Terrell counter-rotations, because the Terrell rotation makes it look like the transverse structure is rotated, and the counter-rotation then leaves the transverse structure invariant. So that's another really neat thing about the light front. So the summary so far for this subsection, the Poincare group has a Galilei subgroup. Its algebra is identical to the algebra from 2D non-relativistic physics, and it basically formally explains all the formulas that look like non-relativistic formulas that we've seen so far in these lectures. Light front time is invariant under this subgroup, basically by design. It's the subgroup that P plus is the central charge of, meaning everything commutes with P plus, meaning that P plus is invariant. But X plus transforms the same way as P plus. It's the plus component of a 4 vector, so light front time is invariant under the subgroup. Transverse separations are also invariant under the subgroup, which is really neat. And this allows you to have a spatial temporal description of the internal properties of hadrons, which is something that I'll get into in the next lectures. Thank you all for your time today. I'm sorry for going a little bit over time, but I am open for more questions now.
Thank you very much, Adam. Are there any further questions? Please raise your hand if so. Phil.
Hello.
Adam, very nice. Thank you. I have a question and then a comment. The question is, if you take the Galileo group in instant, you should be able to make a similarity transform on it, which will get you to the Galilean group in light front. Is that correct? It's that C operator you introduced earlier.
Yes.
Now, the question then is, if in light front, the Galilean subgroup conserves P upper plus, then in instant, it conserves whatever that similarity transformation does to P plus. And the question is, what is that?
Well, it would just be
Is it really P0?
It would be P0 plus P3 over the square root of 2.
No,
So
that already is P plus. That's before you make the transformation.
So the C matrix actually is just kind of a convenience thing for if you have a list of components in instant form, say you have P0, P1, P2, P3, C will send the first component to P0 plus P3 over the square root of 2, second to P1, a third to P2, third to P0 minus P3 over the square root of 2. So it basically will just rewrite all of your matrices so that the first component is now the plus component instead of the zero component.
Well, if you're saying that the thing that's preserved in instant is P0 plus P3 rather than P0,
Uh-huh.
what motivated the original Galileo subgroup? They would have identified something as an invariant, and if what you said is correct, they would have discovered that that invariant is not the Hamiltonian. I mean, so what do people do?
Um, well, your P0 plus P3 would be invariant. Your T plus Z would be invariant. I just can't imagine it being very nice to work. Uh, it's not actually what you're considering time in instant form.
Yeah.
Uh, it, I mean, the Galilean subgroup, you can write it in terms of instant form coordinates. I just imagine it wouldn't be very nice to work with.
Yeah, I was just curious. I mean, there has to be such a subgroup, and it has to
Oh
have
yeah,
certain generators, and there has to be something that as to whether people historically had identified what it
I
was.
yeah, that's a good
That was my
question.
question.
So, not a historian of science, but I do sometimes like to read older papers, and as far as I can tell, people only really seem to have taken notice of this while working with light front. Maybe
I
light
see.
front just makes it a lot more obvious and a lot easier.
I see. Thank you. Now, that was my question. Now for the comment. Very early on in your talk this morning, you talked about in light front, you can see both the present and the past. If you could put that view graph up again. I think it was like the third or fourth one that you showed us.
Um, Was it one of the summary ones, this one?
There it is.
Or
Yes, everything's present instead of past. Now, a few years ago, I looked at the following question.
Mhm.
We do non-relativistic Schrödinger equation. We introduce a time dependence and which is the local time change of the wave function, and a boundary condition on the behavior of the wave function in asymptotic space. And asymptotic space and local time are not inside each other's light cone. And I was very puzzled about that. But then I realized if you write the light cone in instant time, in light front time, you have x plus x minus x perp squared is 0. And if x plus is 0, x minus is not required to be 0. It can be infinite. And therefore, you can have what you've just said. You can look at the present instead of the past, and you have complete information. So in that respect, the Schrödinger equation is more natural in light front than it is in instant, even though that's the way that we always do it.
Hmm. I think I'll have to contemplate this a bit more. I didn't entirely follow, but
Okay. It's written up in that big review of myself, Stanley, and Peter at one point. But
okay.
it was, I mean, it did bother me as to why we can allow Z to go to infinity and get a spatial boundary condition when we've got local time. And why is that? Now, there is another answer, by the way, which I'll give you the Stambrodsky answer, which is
Hmm.
simply that the Schrödinger equation is the non-relativistic limit of the beta-saltpeter equation, and therefore you were already covariant. So I think that's what Stanley would have said had I asked him that question. But yes. Anyway, it's an interesting, that's why I picked up on this comment you made about distant events are considered present instead of past, because that's exactly how we should be doing the Schrödinger equation.
Interesting. Thanks for the comment.
Okay.
Okay, are there any further questions or comments? I don't see any more hands raised. So uh, a recording of this lecture will be posted later today or tomorrow. I'll send the announcement, and The next lecture, as mentioned earlier, will be in 2 weeks' time on Monday, October the 6th. So thank you, Adam, once again for very clear
Thanks.
presentation, and we'll see everybody in 2 weeks.
And my apologies for the typos in the last section.
It's inevitable.